Welcome to EducAgent Studio, where a crew of AI agents help us teach, and you learn with ease. Here's the problem we'll solve today. We will find the LDU triple factorizations of the symmetric matrices A and B, and then explain the special relationship between U and L that happens when the matrix is symmetric. Elimination stores its multipliers in a lower triangular matrix L, and produces an upper triangular matrix U. Then we pull the pivot entries out into a diagonal matrix D, leaving a new U with ones on the diagonal. So L carries the multipliers, D carries the pivots, and U is the remaining upper triangular part, scaled to have ones on its diagonal. Here's the key symmetry bonus. When the matrix is symmetric and elimination proceeds normally, the upper factor is the transpose of the lower factor. That turns LDU into the symmetric form LDL transpose, which we'll verify in both examples. Let's factor the 2x2 matrix A using elimination. The first pivot is the top left entry, 2. To eliminate the 4 under the pivot, we use multiplier 4 divided by 2, which is 2. Subtract 2 times row 1 from row 2, and the second row becomes 0, then 3. The result of elimination is the usual upper triangular matrix. The multiplier 2 goes into L below the diagonal, with ones on the diagonal. The pivots are 2 and 3, so those form the diagonal matrix D. We scale U so it has ones on the diagonal. Dividing the first row by pivot 2 turns the 4 into 2 above the diagonal. That gives the complete LDU factorization of A. And because A is symmetric, we see U matches L transpose exactly. This is the symmetric LDL transpose form. Now we repeat the same elimination and split process for the 3x3 symmetric matrix B. The first pivot is 1, which makes the first elimination step very clean. To clear the first column below the pivot, we use multipliers 4 and 0. Row 2 becomes 0 in the first position, and the remaining entries become -4 and 4. Now we move to the second pivot in the 2-2 position. The next pivot is -4. To eliminate the 4 under that pivot, the multiplier is -1. Adding row 2 to row 3 wipes out the 4 and leaves a final pivot 4. That's the usual upper triangular matrix after elimination. Place the multipliers 4 and -1 into L below the diagonal, with ones on the diagonal. The pivots are 1, -4, and 4, so those go into the diagonal matrix D. Divide each row of U usual by its pivot, so the diagonal becomes all ones. That turns the 4 in row 2 into -1. This is the LDU factorization of B, and once again, symmetry shows up as U equals L transpose. That's the symmetric LDL transpose factorization. The core workflow is elimination. Multipliers build L, and the elimination output is U usual. Then we separate the pivots into D so that U has ones on its diagonal. For symmetric matrices, when elimination needs no row exchanges, the upper factor mirrors the lower one. U is exactly L transpose, giving LDL transpose. These two examples show the same pattern. Compute multipliers, read off pivots, and the symmetry forces U to match L transpose. Watch the next video to see how row exchanges, zero pivots, and stability issues change the picture, and how to adapt LDU when elimination can't proceed so cleanly.